Hello everyone, in this video we are going to see the parity generator and parity checker. So basically it is used in wireless communication system. So when the transmitter has to send some data to receiver, that time there may be chances that due to this channel or due to this free space or due to this air channel, okay, the noise may be added into the sent message. Okay, so considering that the transmitter is sending 11001 to receiver and the receiver receives 10001, so here this second bit is changed here. Okay, so the transmitter and receiver has the same kind of parity generator and parity checker. So if the transmitter is sending the message using even parity, then receiver has to receive the data and check whether that even parity data is received or not. Okay, so the parity generator is taken place at the transmitter side and parity checker is done at the receiver side. Okay, so this is just the introduction about the parity generator and parity checker. Now we will see the two types of parity generator and parity checker. Let us see even parity generator. Now in even parity generator, suppose we want to send this 3-bit information, or we will say these are the message bits. Okay, message bits, and while transmitting these message bits, the transmitter does not send only these message bits, but it sends the parity bit along with this message bit. Okay, so for even parity generator, the transmitter has to send even number of ones. Okay, so that means if there are odd number of ones available in the message bit, then the even parity generator will add 1 into this bit. If the number of ones in the message bits are already even, then parity will be 0. Okay, so in these 3 bits 0 0 0, there are even number of ones, that means 0 number of ones. Okay, so parity bit will become 0. For this combination 0 0 1, odd number of ones, so to make it even parity, the parity bit has to be 1. Okay, so here 0 1 0, odd number of ones 1, that means parity bit has to be 1 to make it even. Okay, so 2 number of ones, so no need to add 1 here. If odd number of ones, parity bit should be 1. Even number of ones 0, even number of ones 0, odd number of ones 1. Okay, so this is how we can generate the message has to be transmitted. So actually the transmitter will send these 4 bits. Okay, 0 0 0 0 0 0 1 1 like this. Okay, now to build this or to design this transmitter circuit or parity generator circuit, just concentrate on when the parity bit is being 1. So for this combination 0 0 1 0 1 0, okay, for these combinations, then for this combination and for this combination. So by seeing this output 1, we can directly say that this is the truth table of XOR gate. Okay, so by XORing of A, B, C, we can obtain the P bit. Okay, so here we can simply draw the XOR logic operation. So this is our A, B, and finally this will be XORed with C. Okay, so this will be our P bit. So this is how we can design the even parity generator. Now let us see the even parity checker. Now let us see even parity checker. So here the X, Y, Z and P, so these are what? The received bits at the receiver side. Okay, so these are the received actual message bits and this is the parity bit. Okay, parity. And what is this C? The C is for checking purpose. So this C bit will become 0 if this number of ones in these 4 bits will be even, okay, and C will become 1 if the number of bits in the message plus parity bits will be odd, okay. So here in this first combination number of ones are even, that means number of ones are 0, so C bit will become 0. So when C bit will be 0, it indicates that there is no error, and if C bit equal to 1, then it represents there is an error. So here in this second combination number of ones are odd, so C bit will become 1, that means for odd number of ones C will be 1, for even number of ones the C will be 0. So here odd number of ones 1, even number of ones 0, odd number of ones 1, even number of ones 0, even number of ones 0, odd 1, odd 1, even 0, even 0, odd 1, even 0, odd 1, odd 1, and even 0, okay. So this is how we can design the parity checker circuit, okay. So from this again you can simply see that when the output checker output is being 1 and when the checker output is being 0, so here for odd number of ones the checker output is being 1, that means at the even parity checker side, that means at the receiver side, again we have to perform the XOR operation of X, Y, Z and P bit, okay. So here by using the simple XOR gates we can design the even parity checker circuit. So here X, here will be Y, here will be Z and here will be P, okay, and finally the output of XOR of first XOR gate and second XOR gate will be again XORed, okay, and it will be given to, or it will be taken as a final checker output, okay. So when C will become 0, when C will be 0, no error, and when C will become 1, then there is an error, okay. So like this we can design the even parity checker circuit, okay. Now let us see the odd parity generator, okay. So consider that we want to send this 3-bit information, or we can say that this is the message bits, okay, message bits. And what is this P? P stands for parity bit, okay. The transmitter will not send only the message bits, but it will send the parity bit also, okay, because the receiver should come to know that whether the received data has any error or not. That's why the additional bits, that is parity bit, must be sent along with the message bits. So here odd parity generator means if the number of ones in the message bits are odd, then parity bit will become 0. If number of bits in the message bits are even, then to make it odd parity, the transmitter will make this P equal to 1, okay. So let us start with the first combination. So 0 0 0, that means this number of ones in this bit format are even, that means the P bit should be 1 to make it odd number of ones in these 4 bits, okay. Then in the second combination number of ones are odd, so already it is in odd parity, so no need to add here 1, so it should be 0. Then odd number of ones, keep it as it is, even number of ones, make it odd, okay. Then odd number of ones, keep it as it is, even number of ones, add 1, okay. Then even number of ones, add 1, odd number of ones, no need to add 1, okay, so 0. Now by seeing this truth table, you can directly say that for even number of ones the output is being 1 and for odd number of ones the output is being 0, that means this truth table is of XNOR gate. Okay, so we will simply perform XNOR operation of ABC to build the odd parity generator. Okay, or simply we can simply perform the XOR operation of ABC, and finally we can make the complement of the output. Okay, so here finally we can complement the output. Okay, so it will become the opposite of even parity generator. Okay, so here we will obtain the P. Okay, so this is the very simple circuit to obtain the odd parity generator. Okay, now let us see the odd parity checker circuit. Okay, so this is the odd parity checker. So here what is happening, so consider that X, Y, Z, P are the input bits to the receiver. Okay, that means the transmitter is sending this 3-bit message along with this 1-bit parity. Okay, so here message bits and parity bit. So P is for odd parity. Okay, so that means if the number of ones in the XYZ are odd, then P will become 0. Okay, likewise, so here the final column is for C. So C is for checking purpose. Okay, checker. So checker output, or this checker output will become 1 if there is an error, and checker output will become 0 if there is no error. Okay, so let us start. So in the first combination, first received 4-bit data, number of ones are even, that means there is an error, so C will become 1. Okay, in short I want to say that if number of ones in these 4 bits are odd, then output C will be 0. If number of ones in these 4-bit combinations are odd, then output will be 0, and if the number of ones in this 4-bit received combination will be even, then output C will become 1. Okay, so let us see. So this 4-bit combination has odd number of ones, so output will be 0. Here odd number of ones, output will be 0. Even number of ones, output will be 1. Odd number of ones, output will be 0. Even number of ones, output will be 1. Even number 1. Odd 0. Odd number of ones 0. Even number of ones 1. Even number of ones 1. Odd number of ones 0. Even number of ones 1. Odd number of ones 0. Odd number of ones 0. Even number of ones 1. Okay, so this is how we can write the truth table for odd parity checker. Okay, now we have to build the circuit to check whether it is odd parity checker or not. Okay, so you have to simply observe that for which combination, for which 4-bit combination the C output is being 1. So obviously this truth table is of XNOR gate. Okay, so we can simply build the XNOR operation of X, Y, Z and P. Okay, so let us start to design. Here will be first XOR, here will be second XOR, finally third XOR. I am just drawing the XOR gates, and finally I will just complement the output, final output. Okay, so here will be X, here is the Y, Z and P. Okay, and finally the C will be what? Complement of XOR, so we want XNOR. Okay, so here will be C. Okay, so this is how we can design the odd parity checker, or simply you can, instead of using this final XOR and NOT gate, you can simply use here XNOR gate. Okay, so I will just redesign this circuit. drawing the same circuit diagram using XNOR gate. This is our first XOR, this is our second XOR, okay, and finally the third XNOR gate. Okay, so see, X, Y, Z, P, and this output of first XOR and second XOR will be given to third XNOR gate, input of third XNOR gate. So this is how we can redesign the odd parity checker. Okay, so here we are going to stop this video, and if you have any difficulty, any doubt, then please write it in the comment box. If you are new to this channel, then please subscribe to the channel, and if you liked this video, then please share this video, okay, so that we can help to the maximum. Thank you.